but instead of an arbitrary point, is the position vector of this foot or perpendicular. Usually we call foot or perpendicular F, because foot. Then the position vector of this foot or perpendicular will be vector OF. Okay, and notice that I call it, I write down for some lambda, because it's a specific lambda. Okay, we have to be careful. It's a because it's a specific value of lambda. It's not any lambda. Unlike our line equation, when we are talking about all those points, all those position vectors, as for all, or rather for some, for any lambda in R, right? In this case, it's for some, for a specific lambda in R, right? That gives us the position vector of this point. Okay, so because it's a specific value of lambda, that gives us the position vector, okay, of the FOP, foot or perpendicular. Okay, so this is how you get started. You need to say that the foot or perpendicular is on the line, and then that implies that we can just write down this equation. Okay, that's the first thing. The second part is that the foot or perpendicular is the vector, okay, the vector where it falls. Okay, so the rock A falls straight down to the floor, right? So vector AF is how it falls. It's like the instruction that the universe tells the rock to fall. The universe tells the rock you have to fall along this vector. This path, this vector, is perpendicular to the ground, or in this case, L line. Okay. So because it's perpendicular, we write it down. Okay. Because it's perpendicular, so the dot product, okay, vector AF, the path that you fall, is when you dot it to the direction of the line, is 0. Why? Because there's nothing similar, okay? Nothing is similar about the path to the line. Neither is it dissimilar. It's neither here nor there, right? It's not like, okay, like the line is like, you know, the direction of the line is here, right? The direction of the line is here. If your vector is like this, then it's somewhat similar, right? They're kind of pointing in the same direction. If your vector is pointing, let's say, like that, then it's kind of opposite direction, because one points that way, one points that way. Okay, it's dissimilar, it's like opposite direction. But in this case, it's neither here nor there. It's just perpendicular. Okay, so your dot product, which is some sort of measure of similarity, it tells you nothing. It's neither here nor there. You can't tell whether it's similar or like dissimilar, like opposite. So it's just equal to 0. Okay, so this dot product is equal to 0. Okay, this is your next part. Okay, now you're going to combine these two facts into one. So because you have some expression for your position vector, you're going to put that position vector, okay, into here. How? Your position vector, vector OF, okay, and you know your position of the rock, right? The position vector will be vector OA. You can use those two to find vector AF. Then you can write down vector AF is vector OF minus vector OA. You do your dot product, it must be equal to 0, right? So you kind of sub one into the other. Okay, you sub this into this. Sub. Okay. So once you substitute, you get this. You get an equation. All you need to do is you need to solve it. Okay. So you expand it out. Okay, you expand this whole thing out. In question, you have numbers. So expand this whole thing out. For example, let's use this as an example. Okay. let's just have A maybe 0, 0, 1. Okay, so that it's easier. Maybe vector T is let's say 1, 1, 1. Okay, whatever. Okay, let's say it's 1, 1, 1. The line is, oh no. Okay, wait a minute. Sorry. Okay. Okay, then now I can't use my mic, so sorry. I can't use my mic. So wait, let me connect my headphone. If it's charged. Oh no, it's low battery. Okay.
Okay. Am I muted? Okay, I'm not muted. Okay, my headphone is low battery, so let's just continue. Okay. Hopefully my iPad charges fast enough. Okay. Anyway, so let's say I have this point, okay, 0, 0, 1. I have a vector that describes the direction of my line. Okay, the direction is 1, 1, 1. Okay. You know what? Let's just call it 0, 0, 1, 1, 0, 0. Okay. So that is easier lah, huh? Okay. Now I want to let this point A fall into my line. My line, I need to write down the equation. Let's say the line equation is R equals to maybe 0, 1, 0 plus lambda 1, 0, 0, okay, T. Okay, then lambda in R. So remember, the first thing we need to write down, okay, the first step is that my, okay, foot of perpendicular F lies on L, okay, which means vector OF is equals to 0, 1, 0 plus lambda 1, 0, 0 for some lambda in R. Okay, second step is vector AF, okay, is perpendicular to vector T, okay, or you can say vector or the line, okay, which means vector AF, okay, dot the position, sorry, vector AF dot the direction vector of the line is going to be equals to 0. Vector AF is vector OF minus vector OA. Okay, so we have this equation. Okay, then let me add a page. Okay, so step 3. Okay, step 3, you sub the vector OF into the equation that you just got. So this is 0, 1, 0 plus lambda, oops, sorry, lambda 1, 0, 0, okay, minus vector OA. Vector OA is just the position vector of this point, 0, 0, 1. So 0, 0, 1. Then the whole thing dot vector T, which is 1, 0, 0. This is equals to 0. You just need to solve for lambda. Okay. So let's write it out. Hopefully nothing goes wrong. This is 1, 0, 0 equals 0. Over here, this is lambda 1, 0, 0, 1. This is negative 1. So lambda equals 0. Oh, yeah, okay. In this case, it's because the numbers I picked are like nonsense numbers lah. So anyway, if lambda is 0, then therefore, okay, therefore F, okay, or vector OF is equals to sub back into this one. Okay, sub back into this one. So I'm gonna point back, sub. Okay. So if I sub back into that one, I will get 0, 1, 0 plus 0 times 1, 0, 0. This will be 0, 1, 0. Okay. This means that F has the coordinates 0, 1, 0. Done. So foot of perpendicular, yes, this step can get a little bit more tedious if the numbers aren't so nice, but the idea is always the same. You follow these same 3 or 4 steps, you will get your foot of perpendicular. You must remember how to find foot of perpendicular, because if you don't, there are some other questions that you won't be able to solve if you don't know how to find foot of perpendicular. For example, okay, not this one. Perpendicular distance, I'll talk about it later. Point of reflection. If you don't know your foot of perpendicular, you cannot find point of reflection. Okay, there probably is some other cheap way to find it, but you need to go like one big round and find a lot of different things. Usually you don't learn that in school because it's not fun to do the difficult stuff. It's not gonna do you any good to learn this. So we're gonna learn it the proper way. The proper way is to find the foot of perpendicular. Then you do your ratio theorem, okay, or midpoint theorem. So first step is to find foot of perpendicular. Then you use ratio theorem. Or in this case, midpoint theorem, because the ratio is 1 to 1. Okay, so let's say I continue from above. So, okay. So from 13.4.1, okay, from example 13.4.1, okay, whatever lah, okay. Our foot of perpendicular, okay, was found to be 0, 1, 0. Okay, A is, I think, 1, 0, 0. Okay, I'll scroll up and check. This is R equals to 0, 0, 1. Okay. Okay. 0, 0, 1. This is damn it. Okay, yeah, correct. This plus lambda 1, 0, 0. Okay, lambda equals lambda in R. Okay, so we have this picture here. Okay, now we want to find the point of reflection. So pretend the line is a mirror. You will see your reflection of that rock, right? A prime. Usually we use prime to denote like a newer version of something like, in a sense. So A prime is like the new and edited version of point A, I guess. Okay. So we want to find this point here. How we do this is just using ratio theorem. Okay. You don't need any other point on the line. For example, in this line equation, I have this position vector. That's exactly my foot of perpendicular, unfortunately, right? So do I need to go and find another point? I can if I want to, but I don't need to. Which point can I use then? I just use the origin, wherever it is. I don't care where the origin is. I join this. I join this. Yeah, let me draw properly. I join this. You know what? Let's use the correct colors. Okay. So let's join this with a black one. Let's join this with a red one. Okay. I have this picture. And this is the ratio theorem picture, right? I have this picture, right? It looks exactly the same. Now, the only issue is that, or the only difference is that the ratio is 1 to 1. So let's just write down like this is like 1 unit. This is 1 unit. Okay. So what we do is using ratio theorem, or you can call it midpoint theorem in this special case. Okay, then we just write it out. Ratio theorem tells us how to find the middle point, right? So let's write it out first. Middle point, this is, I take this number, multiply to that side. Okay, so that's the vector OA. So that's vector OA. So 1 unit times vector OA. Okay, let's just write it as like 1 times vector OA. Then I take this number, multiply to red color. That's 1 times vector OA prime. I add them up. I divide by the number plus the number, 1 plus 1. This gives me the midpoint theorem or the ratio theorem. All I need to do is make vector OA prime the subject. So I make vector OA prime the subject. This will be 2OF minus OA. Okay, let me just double check my working. Yes, correct. Okay, then you can get your answer. Done. Okay, so foot of perpendicular is very important because otherwise you can't really do this unless you go and figure out some roundabout way that you can go and find out how to get your reflection. But I won't suggest doing cheat ways like that because that is usually more trouble. Okay, now let's come back to perpendicular distance. There are 2 ways to find perpendicular distance. Okay, so method 1, okay, this is if you have, okay, vector OF, or if you have the coordinates of foot of perpendicular. Okay, so perpendicular distance from point to line. So let's draw a picture from point A to line L. Same picture again. Okay, so if you have point F, all you need to do is just, well, of course, you know, you need to find foot of perpendicular. Okay, then the second step is to sorry, this is just vector AF, okay, modulus. That's the perpendicular distance. This is the perpendicular distance. Okay, done. Okay, so nothing much really because you just need to find foot of perpendicular. Now, second method, maybe I just do in a different color. Let's say you don't have foot of perpendicular. Okay, how can you find the perpendicular distance from A to L? Yeah, from perpendicular distance from A to line L. What you can do, let's just use this because I don't need a picture for the above one. So let's just use this. Let's say I want to find the perpendicular distance without finding the foot of perpendicular. What I do is I just find out a point on the line. A point on the line. Okay, so first step is to find a point on the line. Okay, any point. Any point. Okay, any point on the line. Okay, so let's say, okay, my line equation is, I forget again. I think it's like this. 100. Yes, correct. Okay, so let's say like this. I can sub in any value of lambda to get me some random point, right? Doesn't really matter. Let's say I sub in like 1 or something. Okay, so maybe I sub in, okay, for example, sub lambda equals 1, okay, into the line equation. So what I'll get is the position vector is equals to 0, 1, 0 plus 1, 0, 0. So 1, 1, 0. Okay, so I have a point 1, 1, 0. Okay, let's call this point P. P point P. Okay. Let OP, vector OP equals to this. Okay. Like this. Okay. Now that I have a point, what I can do is I can just find this right angle triangle. Okay. In this right angle triangle, I can write down my vector 1, 0, 0. This is my direction vector of the light. Okay. Now that I have this right angle triangle, recall just now we talked about how dot product, we kind of smash this vector. Okay, so the vector I'm talking about here is vector PA. We can smash this vector PA into the line. But that's not what I'm interested in. I don't want the length of projection. I want the perpendicular distance. So what is the opposite way? That's just cross product. It's just dot product is smashed into the line. Cross product is the ghost, right? So the cross product gives us this. This is vector PA cross the direction of the line, so vector 1, 1, 1, 0, 0. But 1, 0, 0 by right, I need to divide by the modulus of 1, 0, 0. It just so happens that the modulus is 1. Okay. Then my modulus is whole thing. So the idea is that I use modulus of cross product. Okay, cross product of what? Cross product with unit direction vector of line. Okay, so for example, in this case, this will be perpendicular distance is equals to modulus of vector PA cross the unit direction vector. So in this case, let's say I don't know if it's a unit vector. So I need to divide by the modulus. Just so happens in this case, you don't need to because modulus 1. But whatever this is, will be your answer. Okay. So this is another thing to remember. Back when I was a student, I don't like to remember things. So I unfortunately need to learn how to remember foot of perpendicular. Once I memorize that, I just do the long way. Okay. But I can do this the short way also. Both ways are acceptable. Okay, let's move on. Okay, concepts involving two lines. I think I will need to drag this a little bit longer. Let's just speed up a little bit. Okay, concepts involving two lines. There are a few ways that lines can be related to each other. Let's first sketch out a few pictures. Lines can be parallel. Lines can be intersecting, right? Lines can be, let's say, skew, which is neither parallel nor intersecting. So it's like chopsticks floating above each other, but they're not really touching, right? So you can have these three cases. For parallel, what you do is, let's say I have L1, L2, okay, R1, R2 equals to A plus lambda mu D1, D2. Okay, so lambda in R, mu in R. Now what I need to do is to show that D1, okay, is equals to some scalar constant, okay, some scalar times vector D2. Okay. If, okay, so there are two options or two outcomes. If K, if K cannot be, what's the, okay, wait, let me unplug my think it's because I'm charging my iPad. Okay. If K cannot be found, okay, if K cannot be found, what does that mean? That means, well, if I split it into multiple components, for example, 0, 1, 2 equals to K, okay, 3, 0, 4. In this case, K cannot be found, right? There's no such K, okay? i.e., no such K exists, okay? Then L1 is not parallel to L2. If you can find such a K value, then they are parallel. For example, okay. So for example, if I have 0, 1, 2 equals to K times 0, 2, 4, then K can be half, right? So K equals half. K equals half. Okay. So therefore, L1 parallel to L2. Done. So these are the two possible ways. Okay, so two possible ways. Okay. Next one. To find the point of intersection between two lines. Okay, let's just take this. Okay, if I want to find the point of intersection of these two lines, what I do is simply the same thing as what you will do in secondary school. If you have equations of two lines, to solve for the point of intersection, you just equate them and solve. But in this case, you equate them. Okay, it's up here, actually. It's up here. Okay, so you equate them and then you solve. Okay, usually you just let your calculator solve it. So you equate, okay, so you get, for example, some number, okay, let's just put some random number. 1, 2, 3 plus lambda minus lambda plus 2 lambda, for example. Okay, equals to, maybe let's say 0, 0, 4 minus mu plus 3 mu, for example. Okay, then you use GC simultaneous equation solver. Simultaneous equations solver. Okay, so you solve for a value of lambda and mu. If there are no such values, then, okay, if there are no such values, so no consistent set of solutions, then the lines, no consistent, then the lines do not intersect. If there are consistent solutions, then the lines do intersect, and then you just sub in. Okay, so you get lambda equals to something, mu equals to something. Then what you do is sub lambda or mu into L1 or L2 respectively. Okay, either one doesn't matter because both of them will give you the same answer. Okay, so if no such lambda or mu, then not intersecting. Okay, the lines are not intersecting. Now the last one is to prove that two lines are skew. To prove that two lines are skew, we just show that they are not parallel and they don't intersect. Usually the intersection one is the harder one. So you just do the intersection first. If it doesn't pan out, then you just show that it's not parallel. Or check if it's parallel. Okay, so this one we will skip. Okay, so this one I'll just put a tick here. Okay, let's move on. Okay, angles between two lines. Okay, so let's cover this, and I will use this to jump to planes. Okay, so acute angles between two lines. Whenever you want to find acute angle between two same objects, okay, so let's just, my screen is a bit unresponsive. Okay, acute angle between two things, okay, between, okay, if it's same object, if it's same object, for example, okay, two lines or two planes, okay, we use theta equals to cosine inverse, okay, modulus of hat, okay, hat dot hat. So I'm just going to put V and U. Okay, so what are these vectors? These are going to be the vectors. Okay, these will be the vectors that define the object, whatever the object is. If it's line, then it will be the direction vector. If it's the plane, then it's the normal vector. Okay, so if it's different object, okay, different object, different object. So if it's different object, usually it's just one line, okay, one plane. Okay, if you want to find the acute angle between one line and one plane, is only slightly different. It's just, sorry. Okay, it's only slightly different. Theta is equals to sine inverse of that thing. Okay, I'm just going to put V hat, U hat again. Okay, so again, these will be the vectors that define the object. Okay, so if they are different objects, then it will be one direction, one normal. Doesn't matter which way you dot them, it's the same. Okay. Okay, now let's go to planes. Planes, there are a lot more concepts, but the most important part will be understanding how a plane is defined, because all of the concepts will be roughly similar to, in a sense, the way to show or to do these things will be very similar to how we deal with lines. Okay, so how to understand planes? So we're going to do the same approach as how we defined lines. So we talk about lines as y equals mx plus c. We strip down the idea of a line to just two numbers. One that describes, okay, two things. One that describes the direction, one that describes the position. For planes, unfortunately, we didn't learn planes in secondary school, so we can't really draw that analogy or draw that comparison. To define a plane, okay, we are going to use the dot product. Okay, this visualization is going to be very useful for things like distance between origin and plane, distance between planes, like parallel planes, things like that. How to visualize it is, for any plane, okay, for any plane, and there's an origin, right? There's an origin somewhere. Okay, let's say the origin is up there. Okay, let's say the origin is up here. If the origin is up here and the plane is over here like this, okay, the normal to this plane the normal to this plane is going to, the normal to this plane, if we take any point on the plane, so I'm just gonna draw a few dots, blue color dot, green color dot, purple color dot, orange color dot. I'm just gonna try to draw in some like random places. Okay, now I'm gonna use this normal vector. Let's make it a unit vector, just so that it's simpler. Okay, why is it simpler? It's just because I only want the direction. I don't care about the length of that vector. So let me just draw a dotted line. Okay, let's just draw a hole here. This is the dotted line, and then the normal vector. Okay. So this normal vector, I'm going to just shift it to poke through the origin. Okay. Why do I draw all these points? Let's go and draw our position vector of those points. Okay. To draw these position vectors of these points, and then when I do a projection, okay, so the projection of any point in the plane, okay, onto the direction of the normal vector, okay, will be equal, will all be equal. Okay, the projection of any point, okay, onto the direction of the normal will always be equal. So let's see, if I do a projection of the blue color one to the red color one, so I smash the blue color vector into the red color one, I will collect the blue color vector here. Okay, so I collect the blue color vector here. If I smash the, so let me just draw like an arrow or something. If I smash the green color vector into the direction of the normal vector, I will collect it here. Same thing. Okay. Then purple color, same thing. I'm going to smash it up there. I'm going to smash the orange color one into the direction of the normal vector as well. I'll just collect a bunch of, you know, mosquitoes or flies in this one tower, in this one skewer. Okay. So this is how we define a plane. All the points in the plane have this relationship. Okay. Is such that all of the position vectors of the points, when you project it onto this normal vector, you always get the same projection. That's how you define a plane. Okay. Okay. So, okay. Now for the geometrical interpretation question. So if they ask you, what is the geometrical interpretation of, let's say they give you the first equation or maybe the second equation, doesn't really matter. Okay. I'll just point out the difference. The difference is here, the first one is just a vector n. This one, I purposely make it into n hats. N hats is this description that we talked about. Okay. Why is it so useful to make it n hats? Okay, I just realized the n hat is buried underneath. So n hat. This is n hat. Okay. So why is it so useful to make it n hat? It's so that when I project it, I get this bunch of like smashed up mosquitoes, right? When I measure these mosquitoes, okay, or measure these carcasses, I get the distance, the perpendicular distance from origin to the plane. Perpendicular distance, remember, is just how a little stone in the air falls directly into the ground. In this case, the ground is a surface, it's a plane. The point falls straight down into this thing called the foot of perpendicular. Okay, so we see a lot of the same things popping out again. Okay, so let's scroll down. We have again a bunch of ways, different ways to write the same, to describe the same object, which is the plane. Okay, the first way that I did just now is the scalar product form, the dot product form. Okay, how that works is literally writing out the projection is always equals to the same number. So what does this mean? Any arbitrary position vector, when you dot it with the normal vector, or in this case, the one I prefer, the n hat vector, okay, the unit normal vector, you always get the same number. That's how you define a plane. Okay, plane pi, any random position vector, when you dot it to the normal, the unit normal vector, you get the same number. Okay, so let me put it down here and annotate this. Okay, arbitrary, this is going to be an arbitrary position vector. Okay, any arbitrary position vector, when you project, okay, project onto the direction of the unit normal vector, okay, the projection is always equal. Okay, this is the n. Okay, this the interpretation is same distance. Okay, oh sorry, this is not same. It's not same distance. Same projection, and it just so happens that this is the displacement, not just distance. This is displacement of plane from origin. Okay, displacement of plane from origin following the normal vector. Okay, okay, so this is the description or explanation of this scalar product form of a plane equation. Okay, now the two other forms, Cartesian and vector form, can be easily obtained. First one, your Cartesian form, you just write out the dot product. You just write out the dot product, dot, 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 and then you add together, you get a Cartesian form. Okay, how to know if it's the Cartesian form? You just see x, y, z, that's Cartesian. Okay, so this one's simple, but it's not, again, not useful. Okay, so I already wrote down here, but this is not useful. Okay, not very useful. Okay, okay, let's point out, only useful for simultaneous equation solver, in GC, on GC. Okay, this is only useful for this specific case when you do simultaneous equation solver. Okay, now the vector form. Okay, vector form is just a different way to describe your plane. Okay, this is an alternative view of the plane. Let's say I have a plane over here. Let's just draw it smaller. Okay, I'm going to describe it the same way I described line. First of all, I'm going to walk from the origin to the plane. I'm going to visit a point in the plane. Okay, let's call this point A. Let's call this vector vector A. Okay, to describe this entire plane, I need two vectors along the plane but not parallel, like not equal vectors, not parallel to each other. Okay. So these two vectors must be parallel to the plane. That means they must lie flat on the plane, but they cannot be the same vector. Okay. Why do I want this? It means I can choose, I can use these three pieces of information, these three vectors, to get to anywhere on the plane. For example, this green point. If I want to get to here, I just take the little escalator down here. Then maybe I walk one green, two green, sorry, that's blue, not green. I walk one blue vector, two blue vectors, then maybe I walk one red vector, then I get to the green point. I just follow these instructions. By follow, it's just a line, right? This is a line equation. Then I follow one other piece of information. I walk another direction. Okay. So this is another way of describing a plane. I don't find this particularly useful. It's good for visualizing. Okay. It's good for bridging the gap between lines and planes, but it's not useful for any question in H2 math. If you're given a vector form, to convert into the scalar product form, which is the most useful form, okay? So to convert into the Cartesian, sorry, not the Cartesian form, scalar product form, okay? So what you do is you take your U cross V and you treat it as the normal vector. You solve for the normal vector. Okay. Once you have the normal vector, you also have a position vector of a point in the plane. You can make your scalar product form of the equation. Okay. So again, we have a bunch of like describe geometrically this equation. Okay. This one is a lot easier. You just say it describes a plane in which okay, let me just write it out. Off the top of my head, I suddenly forgot what is the geometrical interpretation. Okay, it describes the set of points, okay, whose or with position vectors, okay, such that the position vectors are vector R, you can just name it, okay, vector R, such that the dot product, right, vector R dot n, okay, such that the dot product R dot n for any point, okay, is equal to D, same number. Okay. Then you can just slip in a little bit of, just slip in the mention of a plane. Describes the set of points which lie in the plane. Okay, that lie in a plane. Okay, with position vectors that satisfy this thing. All you need to do is you just literally describe the scalar product form of the equation. You just tell them that any arbitrary position vector, when you dot it with the normal vector, okay, you get a same number. Okay. Sorry, I forgot to mention the R. Okay, so it describes a set of points that lie in a plane. How do I shift it? Okay, that lie in a plane normal to vector n, okay, vector n, okay, with position vectors, whatever. Okay, so you just want to mention that a plane has this normal vector. Okay, all the points in the plane are related to each other in a way that says the dot product of any of these position vectors, when you dot it with the normal vector, you always get the same number. This normal vector is just, yeah, it's just a normal, any vector, okay? You just say that all these points, if you dot it with the same one vector, they give you the same number. All these points are in the same plane, okay? Right, let's move on. Okay, obtaining plane equation, this one I will skip through. All the instructions are here. So to get a plane equation with 3 points, okay, I'll just draw a picture. To get an equation of the plane with 3 points, 1, 2, 3, okay, say A, B, C. Okay, what I'm going to do is I will just find 2 vectors, cross the vectors, so sweep the vectors like this. I'll grow a normal vector. Once I grow a normal vector, okay, which I can call it AC cross AB. Once I grow a normal vector, I can say that any random arbitrary vector, okay, position vector, dot the normal vector is always going to be equal to the same number, because it's always going to be the same number. I take any points position vector, dot it with the normal vector, I'll get a number. Then I solve for the number. Okay, this is how you get the plane equation. Okay, next one. If you have 1 point on a plane, okay, 1 point on a plane, point A, and then I have a line parallel to the plane, or 1 vector parallel to the plane. Let's say the vector is this. Okay, the vector is this. Okay, it's not normal, it's just lying in the plane. Okay, the vector, say vector V. What I can do is, the instructions are here. Okay, so I want to find a vector that lies in a plane, but is not parallel to the vector or the line given. Okay, I think I made a mistake here. It should be given 1 point on the plane and one only line. Line on the plane shouldn't be parallel. Okay, line on the plane. On plane. Okay, so why is this useful? Because if I have a line on the plane, I have a certain direction, right? So let's call this vector D, direction vector. I also have some point on the line, which is also a point in the plane. This allows me to create a new vector, let's say AB. Then now I can take AB cross vector D. This will give me my normal vector. So any arbitrary position vector dot this vector should give me the same thing as, for example, OA dot the same thing. Okay, so you just need to solve for this and also evaluate this. Eventually you will get R dot some normal vector. Okay, some normal vector equals to some number. Okay, so this is how you get the equation of a plane from 1 point and 1 line in the plane. Okay, next one. Okay, given 2 non-parallel vectors or lines that are parallel to the plane. Okay, unfortunately, you need the in the plane. Okay, in the plane or on the plane. Okay, so why is it useful for it to be in the plane or on the plane? It's because you need a point on the plane anyway. If you don't know where the plane is. You only know the orientation of the plane. You always need the position and the orientation or direction. In this case, the normal vector. Okay. So if you have a plane, okay, and you have two lines in the plane, for example. So if you have, let's say, a line L1 that goes in the plane, that lies in the plane, L2 that lies in the plane. Then what you have is some point on L1, maybe point A, some point on L2, maybe point B. You have the direction vector D1, direction vector D2. Okay, then what you can do is you can write down that any position vector of the position vector of any point in the plane, when you dot it to the cross product of your two direction vectors. Okay, why do you do this? Because if you do your cross product, let's put this at this corner. Let's put this at this corner as well. When you do your cross product, okay, do a cross product, you will grow a normal vector. In this case, it will point downwards, but it's not very important. Okay, you get a normal vector. Because you get a normal vector, this will be the normal vector to the plane. This will be equals to any random points position vector. So let's say OA, because OA or point A lies in the plane. When you do your dot product with the same normal vector, eventually you will get R dot N equals to some number D. Okay, so this is another way you can create your line equation, plane equation. Okay, next one. Now you have all the possible concepts. Okay, I will very quickly scroll through. Okay, you have concepts involving one point and one plane. You can find foot or perpendicular. The instructions are here. Okay, so I will come back to this. Okay, let's look through first. For perpendicular, next one is perpendicular distance. Okay, see, it's really similar to one point and one line, right? Foot or perpendicular distance. Then you have reflection. Same thing again. Find FOP, use ratio theorem. Okay, next one. Now you have one line and one plane. You can show that a line and a plane are parallel. How do you show that they are parallel? Okay, let's draw a picture. If you have a line and a plane, so a line L and a plane, let's say they are floating above each other, they are plane pi, then what we want to show is that the normal vector of the plane is perpendicular to the direction vector of the line. So we want to show this so that they are parallel. For example, if I put a shadow of the line, right, it will lie in the plane like this. I want to show that the line, okay, if I let it drop to the plane, it will sit on the plane. It's not going to be it's not going to form an acute angle with the plane. Okay. So how to show this? Let's say I have these two. Okay, I have this let's just note it down. This is the direction vector. This is the normal vector. So I just take the direction vector. Okay, I want to show it's perpendicular, right? Perpendicular means what? It means there is nothing similar or opposite to each other. So it's not like the direction vector and normal vector are very similar. Okay, it's also not that the direction vector and the normal vector are almost like opposites. They are just orthogonal, okay, perpendicular to each other, which means the dot product, which measures how similar they are, okay, should be 0. And if I calculate it, it is 0. Okay, so because it's 0, therefore D, vector D is perpendicular to vector N, okay, which means the plane pi is parallel. Okay, the line L is parallel to plane pi. Okay, so these are all going to be just using the same properties, same concepts that we have covered so far. Okay, there are a lot of them, but I wrote down I list down all the possible things that you can test. Of course, I might have missed out certain things that are maybe less often tested. In which case, if anyone let me know, then I will just add it in so that you have a comprehensive list of all the possible things that can be tested. Okay. Now the next one is perpendicular distance between line and plane. Okay, perpendicular distance between line and plane. I didn't write down the steps. Okay, but first of all, you need to first know that they are parallel. What that means is like this. Okay, it's kind of like skew, right? It's kind of like they are skew. Okay, except it's not really skew because it's a whole plane. Okay, now I want to find the perpendicular distance between the line and the plane. All I need to do, the easiest way, first of all, I draw a picture, I write down my normal vector. Okay, all I need to do now is that I know I have a certain point. Like for example, this one, this is 1, 1, 0. Okay, I also know that I can create some random point in the plane. Okay, so let's see. I want a point in the plane. Okay, so let's write down. First step, consider, okay, the point. You look at this equation. Okay, only the y coordinate has 1 here. If you do a dot product, how can you get a 3? The only way is if you have a 3 here, right? So consider the point, for example, 0, 3, 0. Okay, the dot product is indeed 3. Therefore, 0, 3, 0 lies in plane pi. Okay, so now where is 0, 3, 0? I don't care, just draw a dot here. 0, 3, 0. Okay, I can join these 2 points with a vector. Okay, this vector is going to be 1, 1, 0 minus 0 minus 3 minus 0. Okay, so this is 1 minus 2, 0. Okay, just want to join them with a vector. Okay, so the second step is really find a vector, okay, joining line and plane. Okay, when I say join, I mean just, that takes you from the line to the plane or plane to the line. I'm going to now project this onto the direction of the normal vector. Okay, so the normal vector points in this direction. When I take this red color vector and I smash it into there, what do I collect? I collect a projection. This projection, if I measure it, I get the perpendicular distance. Okay, so I just need to find, find the modulus of projection of vector onto n hat. Okay, be careful, n hat. In this case, n is, from the question, is 0, 1, 0. So let's just write down how to find this. So I take, okay, I take 1, -2, 0, project onto n hat. So 0, 1, 0. By right, I need to divide by this. It just so happens that this one is a unit vector. I find the modulus of this. This is the perpendicular distance. Okay. If you recall, this is exactly the same thing that we did for lines and a point to a line. Okay, same exact thing. Next one, to prove that a line and a plane are perpendicular, roughly similar again. Just draw a picture first. I draw a plane, I draw a line that pokes through the plane perpendicularly. Yeah, like poke through a piece of paper or something. Okay. So what describes the direction of the line? That's the direction vector. What describes the orientation of the plane? That's the normal vector. Okay. For these two objects to be perpendicular, these two vectors must be parallel. I just show that they are parallel. To show that they are parallel, first of all, show that, okay, vector D is equals to some scalar constant, some scalar multiple of the vector n. Okay. So so just consider this. Okay. If K, in a sense, if it is possible to solve for K, okay, then D parallel to N, which means line parallel to plane. Okay. So if not, then D is not parallel to N. Okay, not parallel. Okay, therefore, line and plane not parallel. Okay, I need to better plug in my iPad again. Okay, next one. Okay, need to go very fast. A lot of examples. Almost near the end already. Okay. Yeah. If you're tired, just leave. It's okay. Okay, it's recorded. Okay. But anyway, acute angle between line and plane. Okay, just recall. Okay, recall line and plane. Okay, acute angle. Okay, between two different things. Same object. Okay, you use cosine inverse. Okay, different objects. Okay, like different types of objects, you use sine inverse. In this case, you use sine inverse because it's different objects. Okay. What do you use the sine inverse and cosine inverse on? You do it on the modulus. Okay, modulus of whatever vector describes the direction or the orientation. For example, the direction vector dot direction vector. Okay, I'll just write it as a hat. Okay, so direction. Okay, or normal. Okay, if it's different objects, then it should be D and N. Okay, D hat and hat. Okay, so again, done. Let's go. Next one, length of projection of vector on plane. Okay, if you want to project a vector on a plane, okay, same thing, draw a picture first. Okay, plane, I have a vector. Okay, so a vector like this, 1, 1, 0. Okay, shouldn't draw the points because the vectors can be anywhere. Now what I do is I first bring it down to the plane. Okay, let's say it's just here. Okay, then now the plane has a normal vector. I'm going to put a normal vector here. Okay, n hat. Okay, n hat is 1, 1, 2 divided by modulus 1, 1, 2. Okay, so I have this. Let me check my, okay. Okay, so like this. Now we get a right angle triangle, right? Right angle triangle. So what do? I want the length of projection. I want this part. Unfortunately, I don't know this direction. All I know is that direction. Okay, so I can only project onto that direction. But I don't want that, right? So I project onto that direction, but I don't want that. I want the part that went missing. The part that went missing is the cross product, which allows us to find the soul of the mosquito that disappeared, right? So I'm going to find length of projection, okay, is equals to the vector 1, 1, 0. I'm going to find the missing part. This is the, so, okay, just, let's not write it there. It's the missing component, right? After I smash the, the mosquito into the red color part, the missing component is, I can recover the missing component using a cross product. So I do vector cross n hat 1, 1, 2 over modulus 1, 1, 2. Okay, and I want length of projection. Length, so modulus. So I only want to measure the length. Okay. Okay, so done. Next one. Now I have concepts involving two planes. I can prove that the planes are parallel. To prove that the planes are parallel, the normal vectors must point in the same direction, n1, n2. Okay, so I just show, what was that sound? Oh, okay. I just need to show that the normal vectors are parallel. Okay, so step 1, show n1 equals to kn2 for some k in R. Okay, then, okay, if such a k exists, okay, then n1 parallel to n2. Okay, which means pi 1 or plane 1 is parallel to plane 2. Okay, if not, okay, plane 1 and plane 2 not parallel. Okay, you should say that the n1, vector n1 and vector n2 not parallel first, then you conclude. Okay, so done. Let's go on to the next one. Okay, we're going quite fast. Okay, next one, perpendicular distance between two parallel planes. Okay, the perpendicular distance between two parallel planes is given by this. Okay, what is this? You can memorize this, but if you want, the visualization is, okay, I'll just write down here. So it's good to memorize, okay? So memorize. So because it's a little bit confusing to think about this, but if you want to visualize, it's just, let's say I have plane and then I have a plane, okay? Where could the origin be? If the planes are parallel, the only option is that, okay, so if the planes are parallel, okay, the origin can be in the middle, or the origin can be on one side of the two planes. So outside. Either the origin is trapped inside or the origin is outside. Okay. What's this got to do with anything? We know that if I write our plane equation, okay, if I write our plane equation as, for example, pi 1 r dot n1 hat, okay, r dot n1 hat equals to, let's say, d1, some number d1. And then I write it as, maybe the other plane is pi2 equals to, sorry, pi2 is vector r dot n2 hat equals to d2. What does that mean? That means d1 is talking about this displacement. d2 is talking about this displacement. Okay? They are in opposite directions. When I take d1 minus d2 modulus, I get the absolute different distance between them. Okay, this tells me the perpendicular distance between the two planes, like this. Okay, if the origin is outside, then for example, in this case, this will be d1. This will be d2. When I take d1 minus d2 and I take the modulus, I will get this distance between the two planes. Okay, but it's better to just memorize this. Okay, so but let me just add, sorry, because I need to clarify what is the d1 and d2. So, okay, pi1 is this equals to d1. Okay, pi2 equals to this. Then the distance is given by that. Okay, so this, try to memorize. Okay, I don't think it's worth it to really confuse yourself with this thing. Okay. Also, the reason why it's the same n is just because they are parallel, so the normal vectors are the same. Okay. Now, if you want to prove that two planes are perpendicular, okay, you draw something like this. It's kind of like you open a book, or maybe you think of it as a floor and a wall. Okay, so the normal vectors must be perpendicular. Okay, the normal vectors must be perpendicular. Okay, so show that they are perpendicular. How to show that they are perpendicular? Show n1 perpendicular n2. Okay, using, okay, because if they are perpendicular, when you take the dot product, okay, it should be equals to 0. Okay. Okay. So i.e. show equals to 0. Okay. Next one. Line of intersection between two parallel planes. Okay. What you do is, first thing, yes, is use the GC method. Okay. So first thing is write both equations. Okay, write both equations in Cartesian form. Okay, Cartesian form. Okay, GC simultaneous equation solver. Okay, once you solve for the equations, you should get a line equation. Okay, so form line equation. Okay, I will show an example for the other method, which is to calculate. Let's say I want to find the line of intersection between these two planes. I first write it as, okay, so this is method 1. Okay, the GC method. Okay, the method 2 is the manual method line. Let's call it manual. Okay, so same thing, I write both in the Cartesian form. Okay, Cartesian form. Okay, so in the Cartesian form, my two planes are pi 1 is x plus z equals to, okay, x plus z equals to 3. Okay, pi 2, that's y plus 2z equals to 3. Okay, now let's let z equals 0, for example. Okay, and it can let any of the variables equal 0. I choose z because it's now it becomes a bit easier. Okay, then what I get is x equals to 3, y equals to 3, z equals to wait, hold on. Z equals to 0. Ah, yes, correct. Okay, nothing wrong. Okay, so this, okay, this is a common point. Okay, this is a common point. So I have a plane. Okay, I draw a picture. I have a plane. Okay, plane, and then let's say plane. Okay, a plane like this. Okay, like an open book. Yeah, open book. I think that'll be easier. Okay, open book. Okay, open book. I have found a common point. Okay, a common point. Now the next part is I have a normal vector. I have a normal vector. If I cross those two normal vectors, okay, if I cross those two normal vectors, I will get a perpendicular vector, okay, a vector perpendicular to both of those normal vectors. Okay, so n1 cross n2 gives the direction vector. Direction vector of the line of intersection. Okay, now that I have a point on the line, okay, because that's a common point, right? So I have a point on the line and the direction vector. Okay, therefore, line of intersection is r equals to, in this case is 3, 3, 0. That's the position vector of the common point, plus lambda n1 cross n2. Okay, lambda in r. This is how you get the line of equation. Okay, my iPad is asking me to sleep. Okay, next one, acute angle. Acute angle, okay, we have covered before. Okay, refer to previous parts. Okay, all right. Now, finally, the last page. Okay, three planes. Three planes is a little bit of extra knowledge because I don't think it should be tested at H2 math level. Sorry, I don't think it should be tested in this newer syllabus, 9758. Okay, in the old syllabus, this used to be a common geometrical interpretation type of question. Okay, nevertheless, let's just look at some pictures. How can three planes how can they be related to each other, right? I can have three planes that intersect at one common point. I'm just going to use my highlighter to draw three planes. One plane like this. Okay. So this is kind of like you can kind of tell this is a bit more, yeah, I think this will be a good idea. Okay, anyway, then I have, let's say, another plane that cuts through the red color one, okay? So like this. It may not be very clear, but it's okay. Now the next one, let's say, is like this. Okay, Okay, I'm so sorry. This is not very clear, but if you try to imagine a little bit, unfortunately, you have to do a little bit of homework. You get a point that is common between among all three planes. Okay. Think of it like this. Okay. Open book. Okay. Open book. Then I cut the book slanted, like slanted. Okay. Like this. Okay, I'll try my best lah. Okay. Like this. Okay, like this. Okay, so this part is outside. Okay, this part is outside. Okay, so the red color part I cut through. Okay, so actually this part is popping out. Then like this. Okay. Okay. Basically, you have a point here. Okay, it's quite hard to imagine. Okay, one common point. You just solve simultaneously using GC. Put all three in Cartesian form. Put into the GC. Okay. Okay. Cartesian form. Okay. The next one, intersect at a common line. This one is quite simple. It's just your, like, imagine you open a book. Okay. Then you flip up a page. Okay. Then you have like this, right? You just have from the side view, the side view is like this, like this, like this. Then you have a line here, which is the spine of the book. Okay. This one, you solve for intersection between two planes, which is a line. Then you show that the line lies in the third plane. Okay. I won't do any example for this because I don't think it should be tested. Next one is infinite triangular prism. Basically, the planes look like this. Let me just so this. Okay. I use a different color. This infinite triangular prism is just plane, plane, plane. Okay. So I'm just going to draw like this. Oh man, how to draw? Like the yeah, okay, you get the idea. Okay, it's very hard to draw. Okay, sorry. from the side view, it's like this, okay? Infinite triangular prism. Basically, you just get this, okay? The three, this one is one plane. Okay, this one is one plane. And then this one is one plane. Okay, yeah, okay, this is easier. Okay, three parallel planes. This is the easiest. That's just this, this, this. All you have to do is just normal vector, normal vector, normal vector, all parallel. Okay, so you just show that n1 equals to kn2. Okay, that's the first one. Second one is n1 equals to maybe okay, let's say mu and lambda. Okay, lambda and 3. Okay, so as long as you show that they are all parallel to each other, you get 3 parallel planes. Okay, so we are done with all 3 vectors topics. I didn't expect this to be so long, so yeah. Okay. So we have glossed over some of the examples, but I have covered all of the concepts. It's just that there are some examples. For example, find the reflection of a point in a line. I've shown that. Reflection of a point in a plane is very similar. So please look through them on your own. Okay. I have given the instructions on those that are, yeah, some of the instructions. Okay. So some of the instructions are not given, but please try to do them. The important ones are, hopefully I have written them down. Okay. So the only thing that I didn't cover today, okay, the only thing I didn't cover today is abstract vectors. So how to deal with things like dot product, cross products with only abstract vectors. So that one we will cover in another lesson lah. Either it's a crash course or something. Okay, so that's all for today. Thanks for the people who tried to attend, but yeah, I know it's a very heavy topic, so yeah, okay, so it's okay, right? Okay, I'll stop the recording now.